Greetings to the respected faculty. I am Lasya Mandapati from CSC AI&ML B section. My roll number is 24951866686. And today we're going to explore a curious case where a familiar algorithm, QuickSort, behaves in a surprising way. As many of you know, QuickSort is one of the fastest and most practical sorting algorithms. But what happens when we take this algorithm, write it in Java, and run it on modern processor systems? Surprisingly, the performance is better than what theory predicts, and in some cases, Java even outperforms C++. So, in this step talk, we'll start with the basics of Quicksort, move into its Java implementation, look at multiprocessor architectures, and then examine why the speed up happens and what it means for how we understand algorithms. Let us begin with an introduction. Quicksort is a classic divide and conquer sorting algorithm. It's famous for being very efficient in sequential execution. So efficient that it's often chosen as the default sorting algorithm in many programming languages. For instance, C's standard library uses it, and so do variations in Java's standard sorting routines. However, when researchers began benchmarking Quicksort in Java on multiprocessor systems, they observed something quite unusual. Instead of just performing as expected, QuickSort showed a speed up that wasn't predicted by traditional algorithmic complexity analysis. This is a big deal because it highlights that algorithmic performance isn't just about the program itself. It's also about the programming language runtime, in this case the Java virtual machine, and the hardware environment, which is the multiprocessor system. Before we analyze the unexpected behavior, let's refresh our understanding of Quicksort itself. Quicksort works on the principle of divide and conquer. The process is simple, however, very powerful. First, we divide by selecting a pivot element and partitioning the array into elements smaller than the pivot and greater than the pivot. Then, we conquer by recursively applying the same logic to the left and right subarrays. Finally, we combine. Though in sorting, the combine step is trivial because the recursive partitions already come together in order. The beauty of quicksort is its efficiency. On average, it runs in the order of n log n time, which is optimal for comparison-based sorting. In practice, it outperforms many other algorithms like merge sort because partitioning is cache-friendly and requires less overhead. However, quicksort has a weakness. If pivots are chosen poorly, say always picking the smallest or largest element, the algorithm can degrade to the order of n square. That is why many implementations use random pivots or a median of the three strategies. This theoretical understanding will help us appreciate why performance differences in Java on multiprocessors are surprising. Here is a concrete example to make the quicksort's behavior clearer. If you look above, we start with an array 10, which includes the elements 10, 80, 30, 90, 40, 50, and 70. Here, the pivot chosen is 70. That immediately splits the array into two halves, as you can see on the right. It splits into two halves, numbers smaller than 70 on the left, which include the elements 10, 30, 40, and 50, and numbers larger on the right, which include 80 and 90. Now, quicksort recursively works on each half. On the left, with 40, 50, and 30, the pivot selection continues until each piece is reduced to a single element. On the right, 80 and 90 are separated. This partitioning tree is exactly what makes quicksort efficient. The recursive nature breaks the problem into smaller and smaller chunks until the sorting becomes trivial. And then, when you look back, the entire array is sorted with very little overhead. Now, why am I showing you this? Because later, when we think about multiprocessors, we'll realize that this recursive breaking apart naturally resembles task division across cores. Even though QuickSort wasn't written here as a parallel algorithm, its recursive nature gives it some implicit parallel friendly behavior. Now, let's focus specifically on Java. In Java, QuickSort is implemented in recursive form just as in C or Python. But Java introduces some unique performance considerations. First, recursion in Java is bounded by stack depth, since each recursive call consumes stack frames managed by the JVM. Second, Java manages memory differently. Objects and arrays are handled by the garbage collector, which can affect performance in subtle ways. But perhaps the most important factor is the just-in-time compiler or the JIT. Unlike compiled C code, Java starts with bytecode and the JVM compiles this into machine code at runtime. This means the JVM is constantly analyzing the program as it runs, looking for patterns and optimizing them dynamically. For something like recursive quicksort, this can mean surprisingly aggressive optimizations that improve performance. So, although the algorithm is the same, Java's runtime system introduces a layer of complexity, and as we'll see later, sometimes a layer of advantage as well. Now, let's talk about the hardware side, the multiprocessor systems. This illustration above shows multiple processor cores connected to a shared memory system. Multiprocessors are designed to allow tasks to run in parallel, with cores working simultaneously on different parts of the problem. Now, when we run a sequential algorithm like QuickSort, we wouldn't normally expect multiple processors to help much, unless we explicitly program for parallelism. In fact, without parallelization, multiple cores can even cause overhead due to cache coherence and synchronization. But multiprocessor systems can also bring subtle changes. Cache hierarchies, for example, can sometimes align with how data is accessed, and scheduling by the operating system or runtime may distribute work in ways we don't immediately see. So, the important takeaway is multiprocessors can influence algorithm performance even when the algorithm itself isn't parallelized. Now, this is where things get interesting. When researchers benchmarked Java's QuickSort on multiprocessor machines, they found out that it scaled better than predicted. In other words, the algorithm appeared to be faster and faster as more cores were available, even though the code wasn't explicitly parallel. Now, why is this surprising? Because according to theory, a sequential quicksort should not gain much from additional processes. The overhead of managing threads, caches, and memory usually cancels out any small benefits. But in practice, several factors combine to create an advantage. JVM's just-in-time compiler was optimizing recursive calls dynamically, turning them into efficient machine code. Part- uh, partitioning, partitioning in quicksort aligned well with cache hierarchies, making memory access faster. And the recursive structure naturally balanced workload across cores, even though no explicit parallelization was written. The result? Java Quicksort sometimes even outperformed equivalent C or C++ implementations on the same hardware. This was unexpected because traditionally C and C++ are seen as faster, lower level languages. Let us further analyze the factors that contributed to this. On the JVM side, thread scheduling was smarter on multiprocessors, reducing idle time, garbage collection, reducing idle time. Garbage collection behaved differently, shorter, less disruptive process, since tasks were naturally spread out. On the hardware side, cache effects were significant. Quicksort's partitioning divided arrays into chunks that fit well into cache memory, reducing cache misses. And because partitions were independent, contention across the processors was reduced. So, what looked like a simple quicksort was actually being supported by both the runtime system and the hardware, creating a huge performance gain. This shows us that algorithm performance can be judged by code alone. It's an emergent property of multiple layers. Now, let us talk about how the experiments were designed. On this side, instead of looking at the system architecture again, we're going to focus on the comparison setup. The researchers ran two versions of QuickSort, one written in Java, running on JVM, and another written in C++, compiled directly to the machine code. Both of them were executed on the same multiprocessor hardware under the same operating system with the same input sizes. This control setup ensured fairness so that any performance differences observed were not because of different machines or environments, but because the runtime systems themselves. Here is the performance comparison. If we look at the bar chart above, on a single processor, Java and C++ show very similar performances. But as soon as we move to two processors, Java pulls slightly ahead. And by the time we reach to four processors, Java QuickSort is clearly faster than C++. This graph illustrates the unexpected speedup visually. Notice that Java scaling run is steeper. Instead of hitting overhead or stagnating, performance continues to improve. This was a central observation. QuickSort in Java actually benefited more from multiprocessors than the equivalent implementation in C++. So, what are its implications? First, it shows us that algorithms cannot be analyzed in isolation. The runtime system, in this case is JVM, has a major influence. Second, it challenges the assumption that big O notation fully describes practical performance. Third, it shows us that language choice matters. Java, often considered slower than C++, actually gained advantages from its runtime model in this scenario. Finally, it encourages us to reevaluate how we benchmark algorithms. Rather than just analyzing complexity or running on single core systems, we need to test algorithms under real world multiprocessor environments. That's where true performance differences become clear. Of course, there are limitations. The observed speedup isn't universal. It depends on the JVM version. It depends on the JVM version, the processor architecture, and even the input distribution. Different JVMs or garbage collection settings could yield different results. Also, while Quicksort benefited here, not all algorithms will. Some algorithms may actually suffer from multiprocessor environments if they don't align with cache or scheduling behavior. Finally, this doesn't explicit parallel programming. If you really want to maximize efficiency, designing a parallel quicksort that explicitly assigns tasks to cores will always be more predictable and highly scalable. So, the unexpected speedup is fascinating, but it's not a guarantee in every situation. So, where can we go from here? First, researchers could study other algorithms in JVM on multiprocessor systems. Does merge sort behave the same way? What about graph algorithms? Second, hybrid approaches could be explored, combining parallel quicksort with JVM, tuning to maximize both explicit and implicit speedups. Let's connect this to the real world. Sorting underpins countless applications with database indexing to large-scale data analytics. If Java Quicksort is unexpectedly efficient on multiprocessors, enterprise applications written in Java would see faster performance without changing a single line of code. So, the implications aren't just academic, they affect how Java is perceived in the industry, not just as a convenient language, but as a surprisingly competitive in terms of performance. To summarize, QuickSort is one of the most efficient and elegant sorting algorithms. On multiprocessors, Java's QuickSort displayed unexpected speedups compared to theory and even compared to C++. This happened because of the synergy between the JVMs, JID optimizations, the recursive structure of QuickSort, and the hardware cache and scheduling. The result shows the practical performance depends on algorithm, language, and hardware working together. The key takeaway is never rely only on theory. Always measure performance in real environments because sometimes reality can surprise us and even outperform our expectations. Thank you for your attention. I hope this talk has shown you not just the elegance of QuickSort, but also the hidden complexity of performance in the real world.